Physicists simulate the elusive something from nothing effect with superfluid helium. In 1951, Nobel laureate Julian Schwinger proposed a startling idea. If a vacuum were exposed to an enormously strong electric field, matter would literally emerge from nothing. In this process, now called the Schwinger effect, pairs of electrons and positrons would pop into existence through quantum tunneling. If you like my content and want to listen more interesting science stories like this, then subscribe my channel. And don't forget to share this video with your friends, relatives, and colleagues to spread the knowledge. The catch: the electric fields required are so unimaginably strong that no laboratory experiment could ever generate them. For decades, the Schwinger effect remained a beautiful but unreachable piece of theoretical physics. Now, researchers at the University of British Columbia, UBC, have found a way to mimic the essence of this phenomenon, not in deep space, but in a thin film of superfluid helium-4. Their work, published in PNAS, offers both a fresh perspective on cosmic processes and new insights into the physics of superfluids and vortices, from empty vacuum to flowing superfluid. Instead of trying to bend the universe with unattainable electric fields, the UBC team replaced the vacuum with a superfluid helium film only a few atoms thick. At ultra-low temperatures, helium-4 becomes frictionless, acting almost like an engineered vacuum. In this system, the role of the immense electric field is taken up by the flowing motion of the superfluid, and the particles that emerge, not electron-positron pairs, but vortex-anti-vortex pairs, tiny whirlpools of motion spinning in opposite directions. These vortices spontaneously appear and vanish, providing a laboratory-scale version of something from nothing. Superfluid helium-4 is remarkable, said Dr. Philip Stamp, a UBC theorist in condensed matter and quantum gravity. When it flows as a frictionless film, instead of producing matter particles, it produces vortex pairs out of nothing, more than just a cosmic analogy. Physicists often look for analog systems, laboratory substitutes that mimic otherwise unreachable conditions in the cosmos. The superfluid helium system serves as an analog for vacuum tunneling, offering parallels to phenomena in black holes, deep space vacuums, and even the earliest instance of the universe. But Stamp stresses that the real significance lies closer to home, in changing how we understand superfluids themselves. These aren't just analogs, he said, they're real systems with real physics, and unlike cosmic vacuums, we can actually run experiments on them. Rethinking vortices and quantum tunneling to build their model, Stamp and colleague Michael Desroches had to overcome major theoretical hurdles. Traditionally, physicists treated a vortex's mass as a fixed constant. Their new analysis shows that the mass of a vortex changes dynamically as it moves, a shift that has profound consequences for how vortices behave in thin films, and by extension, how we think about tunneling processes in quantum systems. This insight doesn't just reshape our understanding of superfluid helium. It suggests that similar mass variability could also apply to the original Schwinger effect itself, modifying aspects of Schwinger's famous theory. As Stamp put it, it's a kind of revenge of the analog, implications across physics. By showing how vortices can be created spontaneously from a flowing superfluid, the UBC team has provided both a practical playground for quantum field ideas and a new window into the behavior of two-dimensional systems. Their work connects the physics of condensed matter with some of the deepest mysteries of cosmology. Understanding how vortex mass varies is exciting because it affects our entire picture of quantum tunneling, said Desroches. And tunneling isn't just an exotic physics concept, it plays a role in chemistry, biology, and the very structure of matter. Supported by the Natural Sciences and Engineering Research Council of Canada, the research demonstrates how carefully designed analog systems can push theory forward. It also reminds us that sometimes, by looking in the coldest corners of the lab, physicists can catch glimpses of the universe's most extreme and inaccessible processes.